but I will be here attentive to your comments.
Okay. So the screen is visible, Ravi?
Yes, it's perfectly visible. You can make it full screen so that.
Yes, I'll do that. Yeah. Okay, fine.
Yes, perfect. Thank you.
Okay.
So yes, let's start.
Yeah. So first of all, I would like to thank Ravi for inviting me to give this talk. So today I'll be talking about zero-sum semi-Markov games with probability criterion. So there are many terminologies in the title, which I'll explain as I go along the talk. So hopefully by the end of the talk, all the terminologies will be clear. So this is a joint work with my PhD student, Arnab Bhavak, and my colleague, Chandan Pal. So before going to the actual problem, first just let me give a very brief introduction to stochastic control problem. So a stochastic control problem is basically an optimization problem. So there can be one or more controllers who are trying to control the evolution of a stochastic process by taking some actions. Fine. Now these actions either result in a cost or yield a reward. And the aim of the controller or controllers is to maximize in case it is a reward or minimize in case it's a cost, which is accumulated either over a finite or infinite time horizon. So basically, it's a stochastic optimization problem. Fine, where the state process is a stochastic process and controller, either a single controller or multiple controllers, are trying to control the evolution of a stochastic process by continuously taking some actions. And because of that, it yields either some cost or some reward, and the aim is to maximize in case of reward and minimize in case of cost. Now, as I said, there can be either a single controller or multiple controllers. Today, we will be talking about the problem where there are multiple controllers. So when there are multiple controllers, it's what is called a stochastic game problem. So again, it can be multiple controllers, but I'll be just talking about two controllers. So for two controllers, a stochastic control problem is said to be a stochastic game problem. Now, a stochastic game problem is further classified into two subtypes, namely a zero-sum game where one player is trying to maximize his or her payoff while the other is trying to minimize the same. So one's gain is other's loss. So that's why it's called a zero-sum game. And non-zero-sum game is where both the players are trying to maximize his or her payoff. Fine. So zero-sum, one is trying to maximize while the other one, the opponent, is trying to minimize. While in non-zero-sum game, both the players are trying to maximize his or her payoff. Fine. Now, stochastic control problems have applications in a wide variety of areas in science and technology, namely in telecommunications, queuing systems, epidemiology, finance, and so on. Now, just to give a very simple example of a stochastic control problem, I said it has applications in finance. So let me give you an example from finance. So suppose you have a certain amount of money and you want to invest in certain stocks, or you want to build a portfolio. So a portfolio is basically a collection of stocks. Fine. So you know the evolution of stock prices are stochastic. So it can be modeled by various stochastic processes. So again, it's stochastic, that's important. And now suppose you are trying to invest in, or you are trying to build a portfolio. So what is in your control? So in your control is how much money you want to invest in which stock or which share. Fine. So here the control is basically the amount or the amount of money you want to invest in each stock, and thereby you want to build a portfolio, right? Now, since the stock, so once you build a portfolio, there are certain stocks in certain proportions. So the portfolio will have a certain value, correct? So now, since the evolution of stock price process is stochastic, so now the value of your portfolio is also, the evolution of the value of your portfolio is also stochastic. So you continuously keep modifying how much you want to invest in which stock depending on how those stock prices move. And suppose your aim is to say maximize your wealth at a certain terminal time, say call it capital T. Fine. So that's a very simple example of a stochastic control problem in finance. Fine. Hopefully the example makes sense. Okay. Now, stochastic control problems are considered both for discrete and continuous time stochastic processes. So in discrete time, generally the state process is discrete time Markov chains, while in continuous time, the state process can be continuous time Markov chains, semi-Markov processes, diffusions. So today we will be considering basically semi-Markov processes. I'll define in detail what a semi-Markov process is slightly later. So based on the what kind of stochastic process we are looking at, so you have a discrete time stochastic control problem or continuous time stochastic control problem. Now, as I said, like since the cost or reward functional, which depends on the evolution of the stochastic process, so the cost or reward that you are going to get through your actions depends on the evolution of the stochastic process. Remember, the controllers are basically trying to control the evolution of the stochastic process via taking some actions. Fine. Now, since the evolution is random, the cost or the reward that you accumulate over time, that is also random. So I said it's an optimization problem. So how do you optimize a random quantity? So the obvious or the most naive approach is to optimize the expectation of the random quantity. If something is random, you take the average of it and then you take the expectation of it and then you try to maximize or minimize depending on whether it is reward or cost. But this expectation minimization has the shortcoming that the risk. So expectation is basically the first moment, right? But the risk is generally captured by the variance or the second moment, right? So if you just try to maximize the average, then you are not taking care of the risk. And because of that, the problem is that it is possible that the risk of the optimal control can be quite large, and hence in real life applications, it can be quite a concern. Like you can think of it like this way. So suppose you know that something has say average 5, but that but if some average is 5, that doesn't tell you like how small or big values are there. That's basically you should think of as risk. So if suppose it tells you, okay, the average cost you pay is small, but it may be possible that with even small probability, you pay a very high cost. So that's what is risk. And such things are generally captured by higher moments, in particular as a variance. So if you are just trying to optimize the expectation, that can be a problem, right? So with that motivation, they're like, in order to overcome that problem, which is there with expectation minimization, there are two approaches in literature, in stochastic control literature. First one is what is called the risk-sensitive approach, where the controller tries to optimize the expectation of the exponential of the cost or reward function. So now say suppose the random quantity is X. In the first approach is you try to minimize expectation of X. But instead of that, the risk-sensitive approach tells you that you try to optimize expectation of e to the power x. Now, since e to the power x, if you look at the Taylor series expansion of the function, the exponential function, it has x, x squared, and so on. So it takes care of higher moments as well. So that is one way of taking care of the risk. That's why this is called the risk-sensitive approach. Another approach is what is called this probability criterion approach. In this approach, the controller tries to maximize, or it is minimize in case of cost, the probability that the reward will exceed a given threshold. So you try to maximize that, okay, you fix a threshold a priori, and then you try to maximize the probability that your reward will exceed that certain threshold. That is what is called the probability criterion approach. And in this talk, we will see an example of this second approach, which is the probability criterion approach. Fine. So now a bit of literature review. Now in the discrete time one controller setup, remember there can be either a single controller or multiple controllers. When there are multiple controllers, it's called a game. Fine. Now in discrete time one controller setup, probability criterion has been considered by several authors like White in 1993, Bowakis and Kebi in 1995, and so on. So that is in discrete time. That means the stochastic process that is being controlled is a discrete time Markov chain. Now in continuous time one controller setup, for semi-Markov processes, probability criterion has been investigated by these authors, Sakaguchi and Otsubo in 2010, Wang and co-authors in 2011, and Wang and co-authors in 2013. And for continuous time Markov chain, probability criterion has been studied by these authors in these years. So you can see that all these works are like, most of these works are basically in the last 10 years. So this is now quite a hot area of research in this probability criterion risk sensitive approach is quite a hot area of research in stochastic control theory. Now, so these were all for single controllers. In comparison, in the stochastic game setup, that means where there are multiple controllers, the literature on probability criterion is very less. So there has been two recent works. So in discrete time zero-sum game with probability criterion has been studied by Wang and co-authors in 2017, and non-zero-sum game has been explored by Wang and Guo in 2019. Again, you can see this is very recent work. Now, so that's in discrete time for multiple controllers or stochastic game. In continuous time, zero-sum game for continuous time Markov chains with probability criterion has been investigated by myself and my student Arnav in 2021. But today, so as I said, in continuous time, the stochastic process can be continuous time Markov chains or semi-Markov processes or diffusions. Diffusions is basically solutions of stochastic differential equations. So in continuous time setup for stochastic games, so in 2021, we looked at this probability criterion for continuous time Markov chains. And today I'm going to talk about our very recent work on zero-sum games with probability criterion for semi-Markov processes. Fine. So that's kind of the state of the art. So now let me start with the actual problem, the model description. So what is a semi-Markov stochastic game model? So it has basically 5 components, or it is a 5 tuple. Now I'll explain each of this one by one. So first of all, what is this E? So this E is the state space, which we assume it to be a Borel space endowed with the Borel sigma algebra script E. Fine. So this state space is basically the space in which the stochastic process will take its value. Fine. So here in this case, the stochastic process will be a semi-Markov process. So it will take values in a Borel space, which we will call as E. Now, this D is basically which is Borel subset of E, because it belongs, so the script T is the Borel sigma algebra. So this is the so D is a Borel subset of E, and this you should think of as a target set. So like, for example, like you can think of it as the collection of all bad sets. So basically we will be considering the stochastic control problem until the stochastic process enters the bad state, or you can think of the system fails. That's the motivation for D. So this can be thought of as the set of all bad states of the system, where D complement will be basically the complement of D with respect to E, right? So we'll start in D complement and we will consider the stochastic control problem as long as until it reaches this bad set, the set of bad states, which is D. So you can think of like the system fails. Okay, so things will be more clear as I go along. Now, as I said, like the players take some actions. So this A and B will be the action spaces, so which we will assume it to be countable. And now this AX, which is again a subset of A, and BX, which is a subset of B, will be finite sets. Now, what are these sets? These are basically the set of admissible actions in state X for player 1 and player 2 respectively. So the players will choose their actions based on what state what is the state of the process currently. Now, if the state of the process is X, which is an element in E because the process is taking values in the state space E, then player 1 can choose his or her actions from AX, and player 2 can choose his or her actions from BX. So AX and BX are basically the set of all admissible actions in state X as X varies over E. And the important thing is this AX and BX are finite subsets of A and B respectively. Now, this K is basically the set of all admissible state action pairs. That means what? So this in state X, which all actions are possible to be taken. Fine. So in state X, the player 1 can choose his or her actions from set AX, and player 2 can choose his or her actions from this set BX. Fine. So these are all permissible, these are all admissible state action pairs. Fine. Now, as I said, so this Semi-Markov process is basically a stochastic process. So it will evolve according to some probability, right? So that probability is basically given by this stochastic kernel Q. So if say the state of the current state of the process is say X, and say player 1 chooses action A and player 2 chooses an action B, then what will happen next? So that what will happen in future, or the evolution of the process, will be described by this Q. Now, how is that? Now, again, let me just, before going into further, let me just very briefly tell what happens. So suppose the state at time 0 starts from some state X, and say depending on X, player 1 chooses some action A and player 2 chooses some action B. Now, based on that action, I said that the players are choosing actions in order to control the evolution of the stochastic process. Now, how will that control, or how are they controlling? Now, based on if this initial state is X and the actions chosen are A and B respectively, then so this is basically what is called a Semi-Markov process is a pure jump process. That means it will stay in a particular state for a random amount of time, and then it will jump to a new state. That's how the evolution happens. So it will stay in a particular state for a random amount of time, which is also called the sojourn time in a particular state. And then after that, it will jump to a new state. So that when it will, how much amount it will spend and where it will jump after that is given by this transition kernel Q. Fine. Now, so what is this transition kernel? Now, say if you fix any set S, fine. Now, again, S in the Borel sigma algebra, and if XAB is from this K, which is the state action pairs, then if you fix an S, think of it like this first component you should think of as the time component, and the second component is the state after jump. As I said, it will stay in a particular state for a random amount of time and then jump to a new state, and again the same thing will happen. Fine. And so based on that, so that random time and the state after the jump, that depends on the actions A and B through this stochastic kernel Q. So now suppose you fix a state S. Now think of it, what is the probability? So suppose you fix that, okay, it will jump to the new state will be something in this S. Now the chance you are asking, okay, how long or when the jump will happen? So that's why, so this first component is empty. Now say this is a non-decreasing function. Why? Because the probability that it will, so it's basically like a distribution function. So it is non-decreasing, it is right continuous thing on right continuous real valued function on R plus. Why R plus? Because this is, I said, you should think of it as the time component such that this thing is equal to 0. What does that mean? I said like this first component is how long it will stay. So this thing that Q0 SXAB is equal to 0. This means that there will be no instantaneous jump. That if a process is starting in a state, it will spend at least a positive amount of time in that state. I said it will stay there for a random amount of time. But what this first assumption is telling is that it will at least spend a positive amount of time. Fine. Okay. And now say, so here, so if you fix the S, then all these properties. Now say if you fix a T, now say you are saying that, okay, what is the probability that jump will happen within time T? That it will spend a time like less than or equal to T. Then if you do that, and it will go to some new state. Now see, there is no guarantee that the process will jump within time T. That's why this is what is called a substochastic kernel. That means if you plug in, so this is not a probability measure, but a sub-probability measure. Why? Because as I said that if you just say that, okay, what is the probability that it will jump within time T? That need not be 1, right? It might jump after time T as well. So if you fix this T, then this is a substochastic kernel on E, because it will obviously jump to some new state in E. Remember, E is the state space. So that's why this is a substochastic kernel. And now if you say, instead of T, if you say infinity, that means it will jump at some fine, like it will jump. Now if you just look at the second component, then you are looking at what is the probability that it will jump to a new state. Like if you fix a set or a Borel subset of E, what is the probability it will jump to that? Now, since I have replaced T by infinity, now this has become a stochastic kernel and not a substochastic kernel, because if there is no guarantee that it will jump within time T. But if you take your T to be infinity, then you are saying, okay, it will jump at some time. And we are looking at trying to find out the probability or the distribution of the state after the jump. So that will be a stochastic kernel on E, on the state space of the stochastic process. Fine. Okay. Now let me describe the evolution in slight more detail. So say if actions A belonging to AX and B belonging to BX are selected in state X by player 1 and 2 respectively, then what is this QTSXAB? This is the joint probability that the sojourn time in state X will be less than or equal to T, and the next state will belong to S. So that's what I said. It will stay for a certain random amount of time, and then it will go to a new state. So this QTS is basically the joint probability that it will stay in state X. Remember, you are starting from X, and the action chosen are A and B respectively. Then the probability that the next jump will happen before time T, and the state after the jump will belong to S, where S is some Borel subset of E, is given by this quantity. So now hopefully what this Q means is clear. Fine. And so in this, so I have explained all this. So the last thing is this R. This R is basically the reward function. So it is a measurable function from K, which is the admissible state action pairs. So this denotes the reward rate. And so what is this? So this is representing profit for player 1. So the problem that we are considering here, player 1 is trying to maximize and player 2 is trying to minimize. So this reward is basically, this is the rate at which player 2 pays player 1. Fine. So this reward rate is, this represents profit for player 1 and cost for player 2, and we are assuming that this Rx-AB is strictly greater than 0 for every x in D complement. So if the state is a good state, so it is not in a bad state, then the player 1 gets a positive reward from player 2. Fine. So player 1 is trying to maximize the accumulated reward, and player 2 is trying to minimize the accumulated reward. Fine. Okay. Now the evolution of the game. So again, this I was just telling very briefly. Now let me tell it in full detail how the process actually evolves. Now, if the system is in state x0 at time t equal to 0, and say the decision makers has a common profile goal lambda naught in mind. I said like probability criterion means what? Player 1 is trying to maximize the probability that his or her reward will exceed this initial this profit threshold lambda naught, and player 2 is just trying to minimize that probability. Fine. So initially both the players fix a common profit goal which we call as lambda naught because it is at time 0. Fine. So this represents reward level for player 1 and cost level for player 2. Now at time 0, player 1 chooses an action A0 from AX0 because X0 is the initial state, and player 2 selects an action B0 from BX0. Remember, AX0 is the set of all admissible actions in state X0 for player 1, and BX0 is the set of all admissible actions for player 2 in state X0. So player 1 chooses, say, some action A0, and player 2 chooses some action B0. Based on what? Now, based on what they are choosing their actions, based on the system state X0 and the profit goal lambda. Fine. Okay. Now, as a consequence of these actions, the system remains in X0 until time T1, at which point the system state changes to say X1 according to this transition law, which I have already described in the previous slide. So if say the actions chosen are A0 and B0, the initial state was X0. Because of that, the system, the process will stay at X0 until time T1, and then it will jump to X0. Now, this T1 and X0 are random variables, and their distribution is given by this transition law. Fine. Okay. Now, at time T1, now the process has spent time T1 in state X0. Fine. And now, as I told you, that the reward is, this is the reward rate. So player 1 is continuously getting a reward from player 2. So this is a continuous time stochastic process, stochastic control problem. So at time T1, what is the total reward that has been generated? Remember, this is the reward, the rate, and the time spent in state X0 was T1. So this is the reward generated at time T1. So this represents the profit for player 1 and cost for player 2. Now, so the player 1 has already got this amount from player 2. So now remember, their initial reward was lambda naught. Now already this much reward player 1 has got. So what is the remaining amount of reward? So that is so decision makers are left with the remaining profit goal lambda 1, which is lambda 0 minus r times this thing. So basically the actions are chosen at each jump time. So at times initially the actions were chosen. Now after the first jump, again the players will choose actions. But what at the first jump time, or also this is also referred to as the first decision epoch, the remaining reward or profit level is this, because this is what they started with. Until the first jump time, this amount of reward was accumulated. Fine. Now, what will happen at the first decision epoch? So based on the current state X1, remember, the process has now jumped to state X1 at time, and the jump time is T1. The current profit goal lambda 1. So what all are being taken into account for taking decision? The current state, the jump time, the current profit goal, the previous state, as well as the initial goal. So the entire history is being taken into account, and as well as the previous actions. So based on all this, a second action A1 is chosen from AX1 and B1 from BX1 are chosen by player 1 and player 2 respectively. Because now the new state is X1, so player 1 can choose his or her actions from the set AX1 and player 2 can choose his or her actions from the set BX1. Fine. Okay. Now, since the process keeps evolving like this, so once it starts evolving like this, so we obtain an admissible history Hn of this controlled semi-Markov process up to the nth decision epoch. So how will the history look like? So you are starting from 0, initial state was x naught, initial reward level was lambda naught, the initial actions chosen were a naught, b naught, then you will say jump to x1, the jump time will be t1 and so on. So you up to the nth jump time, this is the entire history where these are the things. So this t0, t1, these are basically the jump times. This xm is what? So xm is basically the state after the mth jump. Am is the action chosen at the mth decision epoch or after the mth jump time by player 1, and bm is the action chosen by player 2 after the mth jump time. Fine. And what is lambda m plus 1? Lambda m plus 1 is basically the remaining reward level after at the mth jump time. Fine. So that's how you define. So you see, like if lambda m was the remaining reward up to the mth jump time, then when at the m plus 1th jump time or at the m plus 1th basically decision epoch, this is the remaining reward level. Fine. Because this is the time spent between the mth and the m plus 1th jump. Fine. Now, this is basically one particular realization of the stochastic process, one particular evolution of the stochastic process. Remember, all these are random. So this I have given you one particular evolution. Fine. Now, let Hn denote the set of all admissible histories. So you collect all possible histories of the system up to the nth decision epoch. Again, this will be a metric space, and you can endow it with the Borel sigma. Fine. Now I am saying that the players are choosing actions. Now they are choosing actions based on some policies or some strategies. So how to define such policies, or based on what kind of policies? So we come to the definition of policies. So a randomized history dependent policy, or simply a policy for player 1, is basically a sequence of stochastic kernels on A given Hn. That means what? See, basically, so what they do is they are choosing actions according to some probability based on the history up to time n. Players are choosing their actions according to some probability function. Fine. So they choose, say, a particular action with a certain probability. That's what is called a randomized history dependent policy, or that is the policy. A randomized history dependent policy. So this is for player 1. That's why you see. And what is the meaning of this? That this is just because the player has to choose his or her act. If the state is xn, then the player has to choose his or her actions from AXN, because that is the set of admissible actions. That is highlighted by this line, that pi n of 1 AXN given Hn equal to 1. So the actions has to be chosen from that set. Now this is, I have defined it for player 1. So similarly, you can define it for player 2. In that case, AXN will be replaced by BXN. Fine. Now we will denote the set of all policies for player I by this capital pi I. Fine. And let Phi1 denote the set of all stochastic kernels on A given E cross R. So these are basically the collection of all probability measures given X and lambda. These are the collection of all probability measures on A, where A is the action space for player 1. And again, this again says that if your state is X, the action has to be from AX. So if you define by Phi1 that, now remember here we are saying that this is entire history dependent. But like choosing So if you have to follow such a policy, you have to keep in mind the entire history of the process. So this can be slightly difficult to actually implement such a policy in real life. So there are some simpler classes of policies. So those simpler classes of policies are, first of all, what is a policy is said to be randomized Markov for player 1 if actually there is a sequence of stochastic kernels such that this pi n is of this form. So basically, if you compare, so here you were taking action based on the entire history, but you say that a policy is randomized Markov if you are just choosing your actions based on only the current state and the remaining reward level. Fine. And as well as the time. So you see this, it depends on n as well. So it depends on the decision epoch as well. This is randomized Markov. Now a randomized Markov policy is said to be randomized stationary for player 1 if psi n is even independent of n. So even it doesn't depend on the time, it only depends on the current state and the remaining reward level. In that case, you say it is a randomized stationary policy. So this I have all defined for player 1. Similarly, you can define for player 2. So what I'll denote by this capital pi I rm and pi I rs, the families of all randomized history dependent, randomized Markov, and randomized stationary policies for player 1 and 2 respectively. So when I is 1, that is for player 1, I is 2, that is for player 2. And now the way I have defined all this is easy to see that this randomized stationary is a subclass of randomized Markov, which is again a subclass of randomized history dependent. But you see this randomized stationary is the simplest class of policies because here, in order to choose your action, you only need to keep track of the current state and the remaining reward. Fine. And you will see that finally this optimal policies, what is optimal policy, I'll describe just shortly, but you will see that finally the optimal policies will be in this smaller class. So in this nice class of policies, which is a randomized station. Fine. Now, see, I have been talking about a process and all those things. So there is this small technical thing. Okay, how do I know that such a process actually exists? So now it turns out that yes, such a process exists, and the existence is given by some technical existence theorem, which is called Tulsia's theorem. So basically, there exists a stochastic process, Sn, Jn, lambda n, an, bn. Now, what are these stochastic processes? So basically, although while describing the evolution of the process, I said you start from time 0, but it is not necessary. You can define any time as your time 0. So here I say, like, suppose the process starts from time s. So s0 is basically the initial time, j0 is the initial state, and lambda 0 is the initial reward level. So this probability says that basically you start from there. And now the probability that at time, suppose at time n, if the entire history is given by hn, then the probability that player 1's action will be equal to A and player 2's action will be equal to B, that is given by these pi n1 and pi n2. Because as I said that the player 1 chooses action A with probability this, and player 2 chooses action B with probability this. So these are the policies. Fine. So given such policies, so such a stochastic process exists, and if you say that if the history is Hn and the players choose actions An and Bn, then the probability that, so this Sn plus 1 is basically the time of n plus 1th jump, or the n plus 1th decision epoch. So that is, the jump will happen within time t, and the next jump will be in state s, is given by this quantity. So this is basically saying that the stochastic process exists, where what are these stochastic processes? Sn is basically the nth decision epoch, Jn is the state after the nth jump time, lambda n is the reward level after the nth jump time, Now, AN is the action chosen by player 1 and BN is the action chosen by player 2 at the nth decision epoch. So these are all the stochastic processes that are involved. Fine. But now you see these are defined with N. So this, it might seem like, okay, it is a discrete time stochastic process, but no, using this discrete time stochastic process, we can define a continuous time stochastic process. But before that, we need one assumption. Now you see, I'm saying that the process, how does the process evolve? It stays at a particular state for a random amount of time and then it jumps. But now in applications, it is natural that you want to avoid the possibility of an infinite number of jumps in a finite time. Now, for that, you need some assumption. So that is basically the assumption. Remember, Sn is the time of the nth jump. So what you are assuming that limit n going to infinity Sn, that is equal to infinity. That means you are saying that in a finite time, there will be only finite number of jumps with probability 1, no matter what the initial condition is and no matter what the policies the players are following. Now, this is an assumption. So what is a sufficient condition for such an assumption? The sufficient condition is given by this proposition. So let me just describe to you in words what it means. What this basically tells you is that with probability at least epsilon, the time spent in each state will be at least delta. So what you are saying is that in each state with probability at least epsilon, the process will stay for an amount of time delta. So if you assume such a thing, then you can ensure that there will be only finitely many jumps in a finite time, right? So this you need. So this is just a technical assumption you need so that you have only finite number of jumps in a finite time interval with probability 1. And this is a sufficient condition for such an assumption to hold true. Fine. Okay. Now, as I said, so suppose now we are assuming that that thing is true, that there is only finite number of jumps. Now we construct the continuous time state processes. Now I said like this is basically a pure jump process. So in between jumps, the state of the process does not change and the players also don't change their actions. They only take actions at the jump times. So this ZT is basic. You define it to be this JN. Remember what was JN? JN was the time after the nth, was the state after the nth jump. So AN was the action at the nth decision epoch, and BN was the action by player 2 at the nth decision epoch. And so this remains same in between jumps. Sn is the time of nth jump, and Sn plus 1 is the time of n plus 1th jump. So in between, the state and the actions remain same. So it's a pure jump process. And this gives you a continuous time process. So, and this continues, so this pair, this ZT, U1T and U2T. So ZT is the state process, U1T is the action process for player 1, and U2T is the action process for player 2. So this together is what is called the controlled semi-Markov process. Fine. Okay. So now we will describe, as I said, so this is an optimization problem. But till now I have not told you what the players are trying to optimize. I have told you, yes, that they are trying to optimize the probability that the reward will exceed a certain threshold. But here in this slide, we describe it properly mathematically. So for that, first we need this tau d, which is basically the first hitting time of the target set d. So this is the first time the stochastic process jumps to a state inside d. Fine. Now, as I said, we will be considering our control problem only up to the time the process enters the set of and jumps to a bad state, or the process or the system fails. So the performance function, obviously it will depend depending on what policies the players are choosing. Based on that, there will be this reward will be generated. So the performance function of the semi-Markov stochastic game under consideration is defined by this. So what is this? This is basically 0 to tau d. So we are considering the problem up to the time the process enters this set d. And this is basically, so you are integrating from 0 to tau d, and this is basically the reward rate. So this is this integration gives you the reward accumulated up to this random time tau d. Fine, because this why tau d is random, because you don't know when actually it will enter this state d, but it will. So this is a random time, and so this is basically the reward accumulated up to that random time. So you are trying to look at the probability that this reward accumulated will exceed the threshold lambda, where lambda is fixed a priori. So from player one's perspective, one quantifies the chance that the accumulated reward or profit will exceed the level lambda. So this x and lambda, x is basically the initial state and lambda is the initial profit goal. So this is basically the probability that the accumulated reward or profit will exceed the level lambda before the failure of the system. That is because we are looking at the problem up to time tau d, while from players 2's perspective, this measures the risk that the cost level will exceed lambda until the failure of the system. So this is the performance criteria. Now, in order to introduce finally the optimality problem, we just need two more quantities. So this is basically, one is called the upper value and the one is called the lower value. Remember, player one is trying to maximize this quantity over all his possible policies, and player 2 is trying to minimize the same over all his policies. So that's why this is supremum over pi 1 belonging to capital pi 1. Remember, capital pi 1 is the set of all admissible history dependent policies, and pi 2 is the set of all admissible history dependent policies for player 2. So this is sup in and this is im sup. Fine. Now this sup in is called the lower value and im sup is called the upper value. Now we know this is a basic fact that im sup or min max is greater than or equal to sup in, right? So that's why we have that I x lambda is less than or equal to L x lambda. This is just because of the fact that im sup is greater than or equal to sup in. Fine. So in general, this Ix lambda is less than or equal to Lx lambda. Now, if this Ix lambda is equal to Lx lambda, then we will call this common function the value of the game. Fine, and which will be denoted by V. Okay.
Subhamay, yes. Rajesh is asking, could you please recall what is E?
Okay, E is basically the state of the process. This Semi-Markov process is taking values in the set E. Fine. So given a stochastic process, there is something called state space where it takes its values. So this E is basically that state space. Is that fine, Ravi?
Yes.
Okay.
Rajesh may be listening to it. No problem.
Okay. So you have this Ix lambda and Lx lambda. So in general, you have this inequality, but if they are equal, then this common function is what is called the value of the game, which is denoted by V. Now here, as I said, player one is interested in maximizing this quantity. This is basically, recall the probability that the accumulated reward will exceed a certain threshold over all his policies pi 1, and player 2 is trying to minimize this over all his policies. Fine. So based on that, so suppose the value of the game exists, that means if this Ix lambda is equal to Lx lambda, so we don't know whether it will be true equality or not, because in general it's an inequality. So suppose the game value of the game exists, then a policy pi star 1 is said to be optimal for player 1 if this thing is true. That means this is the best policy for player 1. Remember, so you see what it says, because what is Vx lambda? Vx lambda is basically im sup. So what this is telling is that this pi 1 star is achieving the supremum. So this is the optimal policy for player 1. Similarly, you say pi star 2 is optimal for player 2 if the infimum is attained at pi star 2. So, or in other words, this is equal to Vx lambda. Fine. Now, if this pi star k belonging to pi k is optimal for player k, that means for player 1 and player 2, then if I look at this pair, this is called a pair of optimal policies, or also it is referred to as a saddle point equilibrium. Now, in a stochastic game problem, the two basic aims are to show that the game has a value and to show that there exist optimal policies for player 1 and player 2 respectively. Fine. And you see, so why you need the value of the game to exist? Because you see the definition of the optimal policies requires that the value of the game exists. So if you are trying to solve a game problem, that means you are trying to show that you are trying to see whether, or you are trying to prove that whether or not the value of the game exists, and and whether optimal policies for player 1 and player 2 exist. So in case you can show that the value of the game exists and a saddle point equilibrium exists, then you can say, okay, the game problem is resolved. Fine. So that's what we will be trying to do. Now, let me just briefly describe how do we proceed to solve this problem. Now, in order to solve, so remember, we are trying to show that the value of the game exists and the saddle point equilibrium exists, or in other words, the optimal policies for player 1 and player 2 exist. Now, for that, we need to describe some function space Fm, which is the collection of all Borel measurable functions on D complement coordinates R, such that this thing is true. Now, how you should think about this, or from where this H function is coming, think of it in this way. So Hx lambda, think of it as this is the probability that if you are starting from state X and your profit goal is lambda, then this is the probability that your profit will exceed that threshold lambda. Now, so if you see, so that's why you can see that why this condition is there. So if lambda is 0, so if your initial profit goal is say less than 0, then obviously, because your reward rate is greater than or equal to 0, then obviously you will exceed that. So it's kind of a trivial case. Obviously, you will not start with a negative profit goal, but just to define it mathematically, we are making this assumption, and this assumption is intuitively very clear, because if lambda is less than 0, then with probability 1, you will exceed that. So think of this Hx lambda as the probability of exceeding the reward level lambdas if the process is starting from state X. Now say given this psi so this script PAX and script PBX, these are basically probability measures on AX and probability measures on BX. Remember why these are coming? Because basically what the policies are basically choosing some probability measures. So the players are choosing actions according to some probability measures. And if you choose some pi 1 and pi 2 in say randomized stationary, then I'm defining this operator. Now, let me try to explain from where this operator is coming. So as I said, like think of this Hx lambda as the probability of exceeding. Now, suppose you start with initial state X and the reward level is lambda. Fine. Now we condition on the first jump time. Now, if the first jump happens after time lambda over Rxb, Rxab. Remember, initially you are choosing the actions A and B, and the process is in state X, and the reward level is lambda. So if the first jump is happening after time lambda over Rxab, that means then you with probability then you will exceed your reward goal lambda, right? Because if you multiply this with remember, this is the time you are spending, and this R is the reward rate. So if you multiply, that means you have spent this much amount of time and you got reward at this rate. So you have exceeded that. So with this, so we are conditioning on the first jump time. So if the first jump happens after this amount of time, and that happens with this probability, then you have exceeded that. Fine. But now if the jump does not happen after that, but if it happens before that time, then there are two cases. If you are if the new state falls in D, then okay, you have jumped before time lambda times Rxab. That means you have not accumulated the reward lambda. So if you jump to D, then the process ends there, because the process now the system has failed and you have not been able to achieve your goal, which is lambda. But if it jumps to some D complement, now you see D complement, say some state Y. Now what is the new state? The new state is Y. Now you have already got this amount of reward Rxab, and now so the remaining is lambda minus Rxab. So now you can think of it from the first jump time. You can think of it, okay, I am starting from Y, and what is the probability that I will exceed this level? So that's from where this is. So this is basically coming from conditioning on the first jump time, right? And now this is for AB. Now if you are, because the players are choosing actions according to some probability measure, here you are just summing up, like this is basically this A is chosen with probability psi A, B is chosen with probability psi B. So you do this. So again, these definitions are just some extensions of this. But if you have understood this, how this first operator is coming, then these are just some mathematical definitions. Fine. And again, so you need this. So basically, this is TABHX lambda is basically what you are doing. You are conditioning on the first jump time, and then so you are looking at beyond the first jump time. If you have already spent enough amount of time so that your reward has exceeded that level, then well. But if you have jumped before that time, if you have gone to D, then you cannot achieve that reward. But if you have jumped to a good state, then again you think of it as the process, like starting from that state and the new reward. Fine. And why we are defining this operator, you will see we will basically characterize the value function as a fixed point of this operator. Fine. Now, again, remember, this is the performance criterion. This we have written down in a slightly different manner. That is why, because so this 0 to tau D, we have broken it from jump to jump. Why we have done that? Because in between jumps, the state is constant. So this we can write it in this way, and then again, just by using continuity property of probability, this just becomes limit n going to infinity probability of this. Now, what is this quantity? This quantity is basically that up to the nth jump time, you are like you have not reached a bad state, and the accumulated reward is greater than lambda. This is the probability of that thing, and that limit n going to infinity. So this you can write it in this way. Fine. Where what is Tm plus 1? This is basically the sojourn time between two successive decision epochs. Fine. So now, since we can write this performance criteria in this way, so motivated by this, we define some functions. So first we define this u minus 1 pi 1 pi 2. So again, why this? That is because think of it like if your lambda is less than 0, then with probability 1, you will exceed the reward level. And this you just define to be this thing, this quantity whose limit you have. Fine. This is if lambda is greater than or equal to 0 and it is equal to 1 if if lambda is greater than or equal to 0, and if lambda is less than 0, you define it to be 1. Now, clearly you see this un satisfies this monotonicity property. Why? Because if up to the nth jump time, you have exceeded the reward level lambda, then obviously up to n plus 1th jump time also you will exceed the nth the reward level lambda, because the reward is non-negative. So if you have already surpassed the level up to the nth jump time, then obviously you will surpass it up to the n plus 1th jump time. That's why you have this, and this is just precisely this thing. This limit is this. So we have defined un in this way. So limit n going to infinity, un is equal to this. Fine. So now we have a lemma, but I don't want to basically go into very detail of this lemma, but let me just point out what is the basic like take home message from this lemma is this last thing. What is this saying? Remember, U psi phi is basically the accumulated reward if player 1 is following the randomized stationary strategy 1 and if player 2 is following the randomized stationary strategy 2. Now, what this lemma is telling you is that this U is a fixed point of this T psi, this operator T psi phi. So U psi phi is equal to T psi phi. So you see, like the accumulated reward, you have been able to characterize it as a fixed point of this operator. Fine. And okay, and another thing is that like this is UN plus 1, right? So UN plus 1 and UN, remember UN plus 1 is basically the probability that like again, so you can already see what this is. So this UN plus 1 and UN are related via this operator T. Fine. Again, these are slightly technical lemmas, but you don't have to get like even you don't have to get too much into these technical lemmas. Just the main thing is that this UN plus 1 and UN are related via this operator T, and this U psi phi is a fixed point, is a fixed point. What I'm not saying that it is the fixed point. What I'm saying is that this U psi phi is a fixed point of T. Fine. Okay. Now, in order to establish the existence of value of the game and the saddle point equilibrium, we need one final assumption, which is that the process will eventually fail. That means no matter what initial state you start from and what policies the players follow, it will tau d is finite with probability 1. That means the system will eventually fail. And again, this is a sufficient condition for this assumption. The sufficient condition says that from each state, there is a positive probability of going to this set of all bad sets. And that is, there is a lower bound on that probability, which is given by beta. Fine. So the assumption is the system will eventually fail. Okay. Now again, so remember what we showed is that this U psi phi is a fixed point. Fine. And here, what was H? H was basically this sup inf thing. Fine. So TH was defined in this way. Now, what this lemma is telling you is that this U pi 1 pi 2 is the unique solution to the to this operator equation. So this lemma said that okay, this is a solution. What this lemma is telling you is that this is the unique solution. Fine. Okay. Now then again, there is one lemma which basically says that this T is a continuous function in psi phi. Okay. But now finally, for the main theorem, we need these definitions. Like we define U minus 1 to be like this and UN to be equal to T of this. Remember, T is the operator which we defined previously. Okay. Now we get our main result. So we have the following. So now this, so if you define this limit n going to infinity UN, so UN is given by this quantity. So U1, you start, so you initialize this way and then you define your UN successively using this operator T. Now, if you look at this limit, first of all, this says that this limit exists and it belongs to Fn. Fm is that thing. And U star satisfies this Shapley equation. What is that means? That which satisfies this equation U star equal to T U star. So where this Shapley equation is. So one thing you see like here, it is, this is basically the same T operator which we defined previously. But you see one thing is that we have said that this sup inf is equal to inf sup. This is where this continuity and all like some again, this sup inf equal to inf sup, we are getting this via some minimax theorem. I don't want to get into too much detail of that, but that is coming from some minimax theorem. But the important thing, what you're saying is that if you define your UNs like this way, and then the limit exists, and that limit is a fixed point of T. Fine. And remember, you already showed that this U pi1, pi2 is a unique solution to T. Now, so U star is basically what you get is that now if you, so this is sup and this is in. Now using this outer maximizer and outer minimizer, so also these are all continuous, compact, all those things are there. So this sup will basically be attained at some psi and this in will basically be attained at some phi. So if you look at those outer maximizers and outer minimizers, what you can do is, so here U star is equal to T of this, where T is like this. Now what this B is telling you that you can find these two randomized stationary policies, which are basically these outer maximizers and outer minimizers, and they exist because of continuity, compactness, all those things. Now then U star, basically you can write it in this manner. Fine. So now U star is this, but what you know that this U star is actually, so you know that this U star is a fixed point of this, but you also know what? You know that this U capital, this capital U, pi1 star, pi2 star is also a unique fixed point of this. So you see that this small U star is a fixed point of this, but lemma 2 told you that this is the fixed point and this is unique. So that tells you that this U star is basically the value of the game and this U star is equal to this. Fine. So this limit is basically the value of the game and this value is given by this. So once you have this, that what is telling you is that this pi1 star is pi2 star are the optimal policies. Fine. So how we have solved the problem? We have finally solved the problem that we have defined this UNs recursively and we have shown that this limit is basically a fixed point of this and that fixed point is the value of the game. And if you look at this outer maximizer and outer minimizer, that gives you the saddle point equilibrium, or this pi1 star is the optimal policy for the first player and pi2 star is the optimal policy for the second. So we have solved the game because we have shown the existence of the value. We have characterized it as a unique solution, unique fixed point of this operator, and we have also prescribed the saddle point equilibrium, which are given by this outer maximizer and minimizer respectively. Fine. That completes the final theorem, and I'll stop here today. So thank you, and so now I'm open to questions.
Thank you so much. Thank you so much. It was a really nice talk. Anybody had a question very quickly because we are late? Huh? Very quickly.
Yeah, thanks for the talk. So I just wanted to know, I didn't see really well what were the hypotheses on R. It was some kind of cost, right? The function R.
R is the, yes, it is a cost, yes. So yeah, so it's just a measurable function on this K. So you see here the thing is that
no, I mean to say, since you are using some min-max kind of criteria, so in one of the variables, usually you need concavity, the other concavity.
Yes, precisely. So if you see, so that's why we have gone to this. So, yeah, let me just go to the thing. So you see, that's why we have, so see this PAX and PBX. So these are actually convex sets. So see, this AX, BX are finite sets, but they may not, obviously these are, but if we go to probability, this collection of probability measures is a convex set. So yeah, thanks for asking the question. So that's precisely the point. That's why, so this convexity and concavity is indeed needed. So basically what you need is this things to be convex, and also these functions are basically linear.
Okay.
So these are linear functions. So that's why you can actually use, because linear functions are both concave as well as convex. So that's why you can use the minimax theorem.
Okay.
So that's why you actually need to go to this randomized setup.
Thanks.
Anybody else has questions? Quickly, please. So if you, yeah, no. Okay, so we stop here, and thanks a lot again, Subhamay, for a nice talk. As you know, this topic is quite interest of mine. So let's be in touch.
Yeah. Okay.
Yeah. Okay.
Yeah. Thanks, Ravi.
Thank
Yeah.
you.
Bye.
Yeah.
Yeah.
Bye bye.
See you.
Yeah. Thank
See
you.
you.
Yeah.
Thanks.
Yeah. Thanks.